term duct bank, while not explicitly defined in the National Electrical Code, industry standards and best practices generally define it as a trench or conduit system that houses multiple electrical cables or ducts. It is typically used to protect cables from damage, moisture, and physical stress. Duct banks are often constructed using concrete, polyvinyl chloride, or other materials. They may include additional components such as rebar, cable trays, and pull boxes. Now let's consider a specific case where multiple runs of 4-inch galvanized rigid conduit are installed in a ditch. Does this automatically constitute a duct bank? The key factors to consider are encasement and the absence of other components. If only a portion of the galvanized rigid conduit runs is to be encased in concrete, this suggests that the concrete is intended for protection from pavement loads rather than creating a duct bank. The absence of rebar, cable trays, or pull boxes further indicates that the concrete encasement is not intended to form a complete duct bank system. An interpretation that the presence of concrete alone necessitates rebar, red concrete, and specific gravel size may not be supported. A specification section entitled Underground Electrical Conduits likely applies to general conduit installations, not specifically to duct banks. So, based on these details, it is unlikely that the galvanized rigid conduit runs in this project meet the typical definition of a duct bank. The concrete encasement appears to be for localized protection from pavement loads and does not require the additional provisions specified for duct banks. Now let us delve deeper into the components and considerations involved in duct bank construction. Firstly, the purpose of a duct bank is paramount. It's designed to provide a robust and protective pathway for multiple electrical conduits, shielding them from physical damage, soil conditions, and environmental factors. The design and construction of a duct bank often involves a concrete encasement to offer substantial protection. Secondly, the materials used in a duct bank are crucial for its longevity and performance. Concrete is a common choice due to its strength and durability. The type of concrete mix, including the aggregate size and the presence of additives, can be specified based on the soil conditions and anticipated loads. Reinforcement, such as rebar, may be added to the concrete to enhance its structural integrity, particularly in areas subject to heavy loads or potential ground movement. Thirdly, the spacing and arrangement of conduits within the duct bank must adhere to relevant codes and standards to ensure proper heat dissipation and prevent overheating. The National Electrical Code provides guidelines on conduit fill and spacing to maintain safe operating temperatures. Adequate spacing also facilitates future maintenance and cable pulling. Fourthly, grounding and bonding are essential aspects of duct bank construction to minimize the risk of electrical faults and ensure personnel safety. Grounding conductors should be properly sized and connected to the conduits and any metallic components within the duct bank. Bonding jumpers may be required to maintain electrical continuity between conduit sections. Fifthly, pull boxes and manholes are integral parts of a duct bank system, providing access points for cable pulling, splicing, and maintenance. These access points should be strategically located to minimize cable pulling distances and facilitate future modifications or repairs. The size and construction of pull boxes and manholes must comply with relevant codes and standards. Sixthly, thermal considerations play a significant role in duct bank design, especially when multiple high-voltage cables are installed. Heat generated by the cables can raise the temperature within the duct bank, potentially reducing cable ampacity and lifespan. Thermal modeling may be necessary to determine the appropriate conduit spacing, concrete mix, and backfill materials to manage heat dissipation effectively. Seventhly, the depth of burial for a duct bank is determined by factors such as frost depth, soil conditions, and anticipated loads. Burying the duct bank below the frost line prevents damage from freeze-thaw cycles. Adequate cover is also necessary to protect the conduits from surface loads and potential excavation activities. Eighthly, proper backfilling and compaction are crucial for the structural integrity of the duct bank. The backfill material should be free of large rocks or debris that could damage the conduit. Compaction ensures that the backfill provides uniform support and prevents settling, which could compromise the duct bank's integrity. Ninthly, documentation and record keeping are essential for the long-term maintenance and management of the duct bank. Accurate records of the duct bank's location, layout, materials, and construction details should be maintained for future reference. These records are invaluable for troubleshooting, repairs, and future expansions. Tenthly, regular inspections and maintenance are necessary to ensure the continued reliability of the duct bank. Inspections should include checking for signs of damage, such as cracks in the concrete or corrosion of the conduits. Maintenance activities may include repairing damaged sections, cleaning pull boxes, and verifying grounding connections. Now let's shift our focus to some common misconceptions and potential pitfalls associated with duct bank installations. One common misconception is that any concrete encasement of conduits automatically constitutes a duct bank. As we've discussed, the mere presence of concrete does not necessarily transform a conduit run into a duct bank. The key differentiating factors are the presence of multiple conduits, the intended purpose of the encasement, and the inclusion of other components such as rebar and pull boxes. Another pitfall is failing to adequately consider thermal effects, particularly when installing high-voltage cables. Overlooking thermal calculations can lead to overheating, reduced cable ampacity, and premature cable failure. Proper thermal modeling and adherence to industry standards are essential to mitigate these risks. Inadequate grounding and bonding is another potential hazard. Improperly grounded or bonded duct banks can create a significant electrical safety risk, increasing the likelihood of electrical faults and endangering personnel. Strict adherence to grounding and bonding requirements is crucial for ensuring a safe installation. Another challenge is improper backfilling and compaction. Poorly compacted backfill can lead to settling, which can stress the conduits and compromise the duct bank's structural integrity. Using the correct backfill materials and ensuring proper compaction are essential for long-term reliability. Another mistake is neglecting to provide adequate access points for cable pulling and maintenance. Insufficiently spaced pull boxes or manholes can make cable installation and repairs difficult and time-consuming. Careful planning and strategic placement of access points are essential for efficient maintenance. Another oversight is failing to properly document the duct bank's location and construction details. Incomplete or inaccurate documentation can make it difficult to locate the duct bank in the future, hindering troubleshooting and repairs. Maintaining accurate records is crucial for the long-term management of the installation. Finally, neglecting regular inspections and maintenance can lead to undetected problems that can escalate over time. Regular inspections can identify issues such as cracks, corrosion, or water intrusion before they become major problems. Addressing these issues promptly can prevent costly repairs and extend the life of the duct bank. Now let us address some specific scenarios and applications of duct banks. In urban environments, duct banks are commonly used to route electrical cables beneath streets and sidewalks, minimizing disruption to traffic and pedestrian flow. These duct banks often incorporate multiple conduits to accommodate future expansion and provide redundancy. In industrial facilities, duct banks are used to distribute power to various equipment and processes. The duct banks may be designed to withstand harsh environmental conditions such as exposure to chemicals or extreme temperatures. In data centers, duct banks are used to provide reliable power and communication pathways for critical equipment. Redundant duct bank systems may be implemented to ensure uninterrupted operation in the event of a failure. In renewable energy projects such as solar and wind farms, duct banks are used to collect and transmit power from the generating units to the grid. The duct banks may be buried underground to minimize visual impact and protect the cables from the elements. In transportation infrastructure projects such as tunnels and bridges, duct banks are used to carry power and communication cables. The duct banks may be integrated into the structure of the tunnel or bridge to save space and provide protection. Now let's consider some advanced techniques and technologies related to duct bank construction. Horizontal directional drilling can be used to install duct banks in areas where traditional trenching methods are not feasible, such as beneath rivers or existing structures. This technique minimizes surface disruption and environmental impact. Trenchless technologies such as microtunneling and pipe jacking can also be used to install duct banks with minimal excavation. These methods are particularly useful in urban areas with congested underground infrastructure. Precast concrete duct bank sections can be used to speed up construction and improve quality control. The precast sections are manufactured off-site and then transported to the job site for installation. Fiber optic monitoring systems can be integrated into duct banks to provide real-time data on temperature, strain, and other parameters. This information can be used to detect potential problems and optimize the performance of the duct bank. Geographic information systems can be used to manage and visualize duct bank data. The Geographic Information System can store information on the location, layout, materials, and maintenance history of each duct bank. Now let's discuss the economic considerations associated with duct bank construction. The cost of a duct bank can vary widely depending on factors such as the size, materials, location, and installation method. A detailed cost analysis should be performed to determine the most cost-effective solution for a particular project. The long-term benefits of a duct bank, such as reduced maintenance costs and improved reliability, should also be considered in the economic analysis. The cost of potential disruptions and downtime associated with cable failure should also be factored into the equation. Now let's consider some best practices for ensuring the safety of workers during duct bank construction. A comprehensive safety plan should be developed and implemented before any work begins. The safety plan should address potential hazards such as trench collapse, electrical shock, and exposure to hazardous materials. All workers should be properly trained and equipped with appropriate personal protective equipment. Regular safety meetings should be held to reinforce safety procedures and address any concerns. The work site should be properly barricaded and illuminated to prevent accidents. Finally, let's consider the future trends in duct bank technology and construction. The use of sustainable materials, such as recycled concrete and bio-based polymers, is expected to increase as the industry becomes more environmentally conscious. The integration of smart sensors and monitoring systems will enable more efficient management and maintenance of duct banks. The development of new trenchless technologies will reduce the environmental impact and disruption associated with duct bank installations. The use of building information modeling will improve the design and coordination of duct bank projects. And finally, the increasing demand for reliable power and communication infrastructure will drive continued innovation in duct bank technology and construction. The National Electrical Code, or NEC, does not offer a specific definition for duct bank. The term is widely used in the electrical industry to describe a particular type of underground conduit installation. In the absence of a formal NEC definition, it is common practice to rely on industry standards, manufacturer specifications, and accepted engineering practices to determine what constitutes a duct bank. This approach allows for flexibility and adaptation to specific project requirements and site conditions while still ensuring a safe and reliable installation. Industry standards and best practices typically define a duct bank as a group of conduits encased in concrete, used for the underground installation of electrical cables. The primary purpose of a duct bank is to provide physical protection for the cables, as well as to facilitate future access for maintenance, repairs, or upgrades. The concrete encasement also helps to dissipate heat generated by the cables, which can improve their current carrying capacity and extend their lifespan. Manufacturer specifications for duct bank components, such as conduits, spacers, and concrete mixes, can provide valuable guidance on proper installation techniques and material selection. These specifications are typically based on extensive testing and research, and are designed to ensure that the duct bank will perform as intended. Accepted engineering practices, such as those outlined in the Institute of Electrical and Electronics Engineers standards and other industry publications, can also be helpful in determining what constitutes a duct bank. These practices provide guidance on topics such as conduit spacing, concrete mix design, and grounding and bonding requirements. In addition to these technical considerations, it is also important to consider the specific requirements of the project in question when determining whether an underground conduit installation should be classified as a duct bank. Factors such as the number of conduits, the size and type of cables, the soil conditions, and the expected loads on the installation can all influence the design and construction of the duct bank. For example, a project that involves the installation of multiple high-voltage cables in a corrosive soil environment may require a more robust duct bank design than a project that involves the installation of a few low-voltage cables in a well-drained soil environment. Similarly, a project that is located in an area with heavy traffic or potential for excavation may require a duct bank with additional physical protection. It is also important to consider the potential for future expansion when designing a duct bank. If it is anticipated that additional cables will need to be installed in the future, it may be wise to install a larger duct bank than is currently needed in order to avoid the need for costly and disruptive excavation work later on. In some cases, it may be appropriate to install spare conduits in the duct bank, even if they are not immediately needed, in order to provide flexibility for future expansion. While the National Electrical Code does not provide a specific definition of duct bank, it does contain a number of provisions that are relevant to the installation of underground conduits. These provisions address topics such as conduit fill, conductor ampacity, grounding and bonding, and protection against physical damage. It is important to be familiar with these requirements when designing and installing a duct bank in order to ensure compliance with the code and to ensure a safe and reliable installation. The National Electrical Code Article 310.15b3 addresses adjustment factors for more than 3 current carrying conductors in a raceway or cable. When the number of current carrying conductors in a raceway or cable exceeds 3, the allowable ampacity of each conductor must be reduced to account for the increased heat generated by the conductors. The adjustment factors are based on the number of current carrying conductors and the insulation temperature rating of the conductors. Table 310.15b3 provides the adjustment factors for different numbers of current carrying conductors. For example, if there are 4 to 6 current carrying conductors in a raceway or cable, the allowable ampacity of each conductor must be reduced to 80% of its value as listed in the tables found in section 310.16. If there are 7 to 9 current carrying conductors, the allowable ampacity must be reduced to 70%. The adjustment factors are cumulative, so if there are both more than 3 current carrying conductors and the conductors are installed in an ambient temperature higher than 30 degrees Celsius, both adjustment factors must be applied. It is important to note that these adjustment factors only apply to current carrying conductors. Grounding conductors and neutral conductors that only carry the unbalanced current from other conductors are not considered current carrying conductors for the purpose of this rule. However, if a neutral conductor carries a significant amount of current, such as in a 3-phase system with nonlinear loads, it may need to be considered a current carrying conductor. It is also important to consider the directing factors specified in the National Electrical Code section 310.15c for underground installations. When conductors are installed underground, their ampacity may need to be derated to account for the higher ambient temperature of the soil. The amount of derating depends on the depth of the burial, the type of soil, and the number of conductors in the raceway or cable. In addition to the National Electrical Code requirements, it is also important to consider any local codes or regulations that may apply to the installation of underground conduits. Some jurisdictions may have more stringent requirements than the National Electrical Code, so it is important to check with the local authorities before beginning any work. When designing and installing a duct bank, it is also important to consider the potential for future expansion. If it is anticipated that additional cables will need to be installed in the future, it may be wise to install a larger duct bank than is currently needed in order to avoid the need for costly and disruptive excavation work later on. In some cases, it may be appropriate to install spare conduits in the duct bank even if they are not immediately needed, in order to provide flexibility for future expansion. Overall, the determination of what constitutes a duct bank depends on a variety of factors, including industry standards, manufacturer specifications, accepted engineering practices, and the specific requirements of the project in question. By carefully considering these factors, it is possible to design and install a safe and reliable duct bank that will provide years of trouble-free service.